In the previous video, I showed you that we could take some dense matrix A and through a series of row operations, reduce it to an upper triangular matrix U. Now, along the way, we store the elementary matrices that we need in order to perform this. Now, if we write this as a matrix multiplication equation, what we can do is reorganize this and get an expression for A. Now, what turns out to happen is that this matrix A ends up being the product of a bunch of inverses times U. Now, those inverses come from the elementary matrices, and we already discussed that all of those inverses exist, and they have a very, very special form. They look almost identical to the E's, except all those off-diagonal entries are negatives. So what ends up happening is this ends up producing a special matrix factorization called an LU factorization. Now, we know that this is U because it ends up creating this upper triangular matrix that we found. But the beautiful part that we showed in the last video is that this lower triangular matrix L, it has the following structure. It has ones down its diagonal, zeros above, like any lower triangular matrix, but we no longer need to compute the inverses and compute their product. What we discovered was that these off-diagonal, the non-zero off-diagonal entries are simply the negatives of what we found in the elementary. So this would be a -2, a -3, and this should be a +1. Now, I think I made an error in the last video with that particular entry. It should be a +1. And this is amazing because now we've factorized this matrix into an LU. But some of you may be saying, like, who cares? What's the point? Why do we care? When it comes to solving a single system, AX equals B, it doesn't really have much advantage for us. It's kind of a neutral step, but when it comes to solving multiple systems, AX equals B, that have the same left-hand side A, this ends up being a huge savings. What we do is we make the following replacement, right? We say, all right, now that we have this LU factorization, we can write our system like this. And what we're going to do is make a substitution. We're going to call this thing vector C. So what effectively happens is that we are going to replace one potentially complex system with two easy or easier systems anyways. And the two easier systems are the following. We are now going to solve LC equals B. We're going to solve this for C. And then we're going to take that answer and we're going to solve UX equals C for the vector that we were interested in the first place. When we solve a linear system, this is what we're interested in knowing. And if we do this two-step process, we will be able to solve it. And these are easier because they're each triangular systems. And when you solve triangular systems, it's actually very straightforward to do it. And as an example, let's solve the matrix that I gave you, AX equals the following. I'm going to have 4, -7, and 12 using the LU factorization. Okay, so the LU factorization works like this. It says, let's take that system we've got and replace it with a two-step process. Number one, we're going to solve LC equals B for some intermediate vector C. And then we're going to solve UX equals that same answer on the right-hand side for X. And that's going to give us the solution that we want. Okay, so the details that we had from before. Step one, we're going to solve LC equals B. All right, so here's the lower triangular matrix that we had. -2, 1, 0, 3, 1, 0. 3, 1, 1, sorry. And we're going to put this right-hand side vector that we've been given over there. Now again, in this matrix, we're taking this factorization and replacing it. Negative 210, negative 311. And this is an easy system. Very easy. C1 is 4. This is going to tell me that C2 is negative 7 plus 2C1. So that's going to be 1. And this is going to tell me that C3 is 12 minus C2 minus 3C1. Well, I already know all those values. So I'll have 12 minus 1 minus another 12. So I'll get a negative 1. So this vector C, which wasn't part of the original problem, is this. And it was very few steps to get that C, right? I didn't have to do any more row replacements. I didn't have to create any zeros anywhere. This is a nice substitution problem. This is called forward substitution. Once I know the first variable, it takes me to the second, and then once I know the second, it takes me to there. So now what I have to do is I have to solve ux equals c for the variable that I really want. Now this is where I use the u that I constructed. U is this 1, 2, 1, 0, 1, 0, 0, 0, 1. And I put this vector that I just found as the answer over on that side. And this process here is going to be called backward substitution. So what does that mean? So I can see that x3 should be negative 1. So I'm starting at the bottom and then I'm going up. Luckily for me, I have a 0 in here, but I have x2 is also 1. And I'm going to put both of those into this top equation. I'll have x1 is 4 minus 2x2 minus x3. So this is going to give me 4 minus 2 is 2 plus another 1 is 3. So what I've just found is that my solution vector here, x, is 3, 1, negative 1. And so the solution to ax equals b should be 3, 1, negative 1. And I found it from 2 separate triangular solves. So this is the whole point. We replace a dense system, ax equals b, with 2 triangular systems. And you might say, that's a waste. Now I'm solving so much, right? I have to find the L and the U, then I have to solve 2 separate systems. Why do I bother with all that? Why shouldn't I just go ahead and solve the system by hand right from the beginning? And if you're solving little tiny systems 3 by 3 by hand, then yeah, it doesn't make a difference. You should just do the row reduction. But in real life, when people solve these systems by computer, when they have to code a computer to do this, it doesn't make any sense to do it that way. And here's why. When you solve ax equals b by going right down to the row reduced echelon form, it's big O on the order of 2/3 n cubed steps, where your matrix here is n by n. Okay, so that's the work that it costs. So if you are into computer science, you can do the algorithmic complexity of something like a row reduction algorithm, the Gaussian elimination algorithm. It's about 2/3 n cubed steps. All right, to find an LU factorization, it costs you exactly the same on same order here. It's about 2/3 n cubed steps. The amount of work to do that is about the same. Now, if you also want to solve 2 triangular systems, people have studied the algorithmic complexity. Solving triangular systems is an order of magnitude cheaper. It costs about n squared for one of those systems, so you need 2 of them. So in the meantime, in the one-off scale, yeah, it's a little more expensive to do it with LU this way. But really where it kicks in is in a situation like this that happens in practice. If we need to solve repeated, and I'll say sequential, systems where they all have the same left-hand side, ax equals b1, ax equals b2, all the way down to, let's say, ax equals bk. So if I have to keep solving the same system over and over and over again, maybe whatever, 100 times or 1,000 times, which does happen in practice, then the real savings kicks in. Because now, if you wanted to do this with row reduction, with the row reduced echelon form, it's going to be on the order of 2/3 n cubed times k. So you're scaling up this k, right? You're scaling up, this n cubed. Now, just for understanding, if n is 100, that's 10 to the 2. N squared would be 10 to the 4, which is 10,000. And n cubed is 10 to the 6, which is 1,000,000. So n cubed is substantially bigger than n squared. Now, if you were to solve that same problem with LU, yeah, you still have to do one solve with the LU. You have to find the LU factors. But once you have them, you have them. They don't change. If the A is the same on all the sides, you just go ahead and keep it. Then, the cost of repeatedly solving those other things, the K gets attached to this thing, to this n squared. And that makes a huge savings. Now, for a sense of how much better this is, it's kind of like asking, if I have 2/3 n cubed, so if this is the number of operations I need to do, how many 2n squareds will fit in it? Well, if you do some simple algebra here, you'll get n over 3. So that means if, let's say, n is 300, that means I get n over 3 is 100. So that means it would be 100 times larger. Holy smokes, right? So just to give you a sense of that, one Gaussian elimination, one row reduced echelon form solve is about 100 times more work than just solving a couple of LU solves, the triangular solves. And that's why people do this. So when it comes time to implementing this with a code, every code that you see as its general purpose solver will code an LU factorization. That's what they do. It costs about the same amount of work as doing a one-off solve. Hey, and if you never use it again, fine. It costs you the same work. But if for any chance you need to use and solve that system again, then it pays off tremendously for you to use LU. So not only is it a practical savings in the amount of work you have to do, it introduces a beautiful result of factorizations which keep coming up in applied linear algebra. How do we implement these things? Factorizations are the way to go.